Dependency parsing is the process of analyzing a sentence structure, which is a fundamental NLP task that is required by many downstream tasks, such as relation extraction and author attribution. And in this work, we want it to happen for the language of Thai. My name is Tay Rutherford. I am from Chulalongkorn University in Bangkok, Thailand. And this work is a collaboration between AI Singapore, Chulalongkorn University, and Prince Songkla University in Thailand as well. First of all, what exactly is dependency parsing? Dependency parsing is the analysis of grammatical structure of a sentence by identifying the dependencies between words. The model that we use for dependency parsing is a tree, like in tree in computer science. So each word is a node, and a node, which we call a head, has 0 or more children, which we call syntactic dependence or just dependent. And the edges between the nodes in the tree is a syntactic relation. It points from a head to dependence. Let's look at an example. This is an example of dependency tree in English. So you can see here that have is the root verb. So that's the root of the tree, and it has quite a few dependents. It has prepositional phrase after more than 10 years of UD as one of the dependents, and it has we as a noun subject. We has finally as an adverb modifier, and finally it has tree bank, which is the head of a noun phrase, which is a direct object of the verb. So in this example, you can see all the relations between all of the words within a sentence, and all those relations form a tree which reveals the syntactic dependencies within this sentence. So what did we do? We made the Thai Universal Dependency Tree Bank, or we call it TUD, and it is the largest Thai dependency tree bank, and it consists of 3,600 something sentences and over 77K tokens, and they are all manually annotated with syntactic dependency relations. And our best dependency parser trained on this dataset, we want to prove that our dataset can work as well. So it achieves 90% unlabeled attachment score, or UAS, and 85 label attachment score, or LAS. I want to show you a little bit of the data that we have created, and before we get to that, we have to understand a little bit of Thai writing script. So I have two versions of the same paragraph that we are drawing from Thai National Corpus. So you can see that there are not a lot of spaces, and in many languages we rely on spaces to mark word boundaries, and also some other punctuation to mark sentence boundaries. And although you might not know Thai, in this example here you can see that there's no punctuation whatsoever, and there are only a few spaces. So to annotate this kind of data, we have to change the top to the bottom, which we segment by words. And also since we want to annotate each sentence, since dependency tree is a model of a sentence, so we also have to segment the data into sentences as well, which has been proven to be not a trivial task to do even with machine learning. But fortunately for word segmentation, we could use machine learning based word segmenter to handle that automatically. So to annotate this dataset, we have to turn to annotating each token by identifying the head, so that we don't have to bother with sentence segmentation directly. Once we found the head of each word in the sentence, then we could try to find separate trees based on the syntactic relations. So we found a bunch of trees, which is a bunch of sentences as part of the process. Besides this, there are many other syntactic theories and issues that we have to adjudicate to be able to annotate this data more consistently. I would show one of the examples, and one of the issues that we had to deal with is a serial verb construction. Serial verb construction is a very common syntactic pattern in the Thai language, which means we stack together, we string together a bunch of verb phrases. So you see like a verb phrase here together, and you see a verb phrase here together. And this one is more clear. You have a verb phrase, and a verb phrase here. And all these four sentences are part of serial verb construction patterns. And we have to treat each structure separately because semantically they're quite different. So the internal structure of it are very different, although on the surface it seems like it's just a bunch of VPs together. So for this first one, we treat it as an XCOM. So this is a VP complement. So which means these two verbs share the same subject. On the other hand, this pattern that we see, the subject of this verb and the subject of this verb don't share the same subject, and moreover, it actually linked to an omitted pronoun which drops a lot in the language. And for this pattern, we call it resultative pattern because the object here is an object of the first verb, but it's also a subject of the second verb. So we have to treat that differently. And finally, the last one, we have this miscellaneous patterns that we cannot really group into a big group, for example. So we kind of treat this as a compound kind of serial verb constructions. And there are many more syntactic issues that we have to get right before we can get a solid annotation scheme. At this point, you might want to know how we train the parser. So people have studied parsing for a long time, and there are many ways, many models that we could use for forming a dependency parser. So we have four questions that we want to tackle here. The first one, which architecture should we use, graph-based or transition-based? They're better for certain languages. Should we need part speech tagger because now that we have much better encoder now? And do we need a super token feature so we can steal the context of the token and make it part of the feature? Do we need that? And how important is an encoder for turning each word into an embedding? So we run a bunch of experiments and try to test all combinatoric combinations of these subcomponents when we want to train the parser and see which one would yield us the best result. It's a really big table, so we turn it into a regression problem. So we regress on the accuracy, which is the UAS and LAS, and a bunch of factors that we try to study. So it turns out if you use open source toolkit, it's highly optimized, so you get around 2 point extra on UAS. And for the architecture, so it turns out if you use transition-based architecture, you beat the graph-based architecture by around 1 point of UAS. And for the encoder, we compare two encoders that are tailored specifically for Thai, and it turns out if you use the one that are trained a bit more, you still gain a point extra. And the augmentation, the super token context doesn't really help you much, so we don't get much of the gains over here. And most interestingly, the parse speech quality. If you get the gold standard, then you get 2 points extra, which is the biggest factor of all the factors that we studied here. And one of the most interesting things here is that if you use no part of speech, it's almost the same as use automatic part of speech tagger. So which means if we can get really good part of speech tagger, we can get a performance gain. But as of now, we don't get anything from using part of speech tagger that is not from the gold standard data. And here's the error analysis. Why is this a hard problem for parser? Because it's the performance is quite a bit lower than English. First of all, we got a lot less data to train on, so that's one of the causes. And we try to look into the actual fundamental grammatical difficulties that the parsers have. So one of the patterns that we saw is that right here. So some of the grammatical words actually can take multiple part of speech tag because that's very characteristic of Thai. So for example, ma and pai could be a diacritic sentence final particles, which we call an adverb here, but it could also be a main verb as well that takes the normal verb phrases. So you could confuse them from the part of speech and then confuse them on the dependency relations. This as well. So these words can both be adverb modifier and can be auxiliary verb depending on where they are and in the context of the sentence. So if these grammatical words are so hard to pin down what role it would take, then it's really hard to find the dependency relations in the sentence. And these are just some of the observations we found when we dig into the errors that the best parsers make. So here's a conclusion. We made the largest Thai dependency tree bank, which you can download here, and it's soon to be uploaded onto the Universal Dependency Project. So stay tuned for that. And we also make the first working Thai dependency parser, which is a graph-based parser based on Stanza, and that achieved the best overall result, although it's not a transition-based parser. And it could be downloaded on GitHub, and if you just want to use it, you could use pip install and use it on Python as well. And for more detail about this paper, please go read our TACO paper, which I will provide in the link below. Thank you.